Good morning, friends. Today I am going to discuss the boundary layer separation. This is a very important topic, and a variety of physical phenomena can be explained by by the boundary layer separation. Uh, mm, so the objective for today's class is the how the velocity profile, boundary layer profiles, behaves in the near the wall, and then I will explain the with the help of these velocity profile the boundary layer separation. At the start, I will show you this slide, and this slide shows variety of physical phenomena. Like the first shows a car where car we're testing on a wind tunnel, and you can see that the off in see the boundary layer separation occurring in the circular zone which is highlighted. There's another car which is more streamlined in approach, and you see very less boundary layer separation or nearly no separation. Then there is an aerofoil which is at an angle of attack, and you can see the boundary layer separation at the stall, and this airfoil is right now at the stall, so the separation will be at the leading edge, which is the start over here. Now there is another separation which I am talking about. There is a separation in a diverging duct. So you can see the separation occurring at this point. So in all these examples, there are open flows where it is placed in a open environment, and the like duct, it is a case where it is placed in a environment in a closed environment. Now there is another physical phenomena like which is called as the drag crisis, and this is also explained with the help of separation. But this separation is there in so if a ball is there, flow over a sphere is there, and you see there is a the separation occurring at a point where which is nearly 90 degree. But if the flow is turbulent, as it has more kinetic energy, it can resist to separation more it shows as below in the angle of separation, the point of separation is further downstream, and it shows that the separation occurs at around 30 degrees, something like that, 45 degree. And this, because of this transition, there is a certain loss of drag, which is called as the drag crisis, which is explained with the help of these two curves. So this is a curve between drag and Reynolds number, and as you see that the number is steadily decreasing, approaching, and then it suddenly drops, and then it suddenly increases. So this happens because of the transition from laminar to turbulent flow. But boundary layer separation is entirely a laminar phenomena. It doesn't needs it is present in both turbulent as well as laminar flow. It doesn't needs to be only present with the turbulence. Some people can confuse with the turbulence and separation, and it is not. Turbulence is nowhere related to separation. Boundary layer separation can occur in a laminar flow as well, which is you can see is in the pictures. So so you can see that there is an example of flow over a transition, flow over a boundary layer. So in this start on a curved surface or a cylinder. So you can see the boundary layer growing. Okay, and then it separates at this point, and before that it is a laminar boundary layer, and after that the boundary layer separated. It may be after that there may be a transition in this zone of transition. The boundary layer could be laminar or turbulent. It is not a characteristic of a boundary layer, but it is a characteristic of the flow Reynolds number. What is the Reynolds number at that that process? Okay. So now I will again review the slides, review the equations which govern this flow. That is the boundary layer equation. So steady flow over a flat surface is governed by these equations, which we have discussed over long time back in our last lecture. Continuity equation is given by these two. The momentum equation is given by this, and the boundary conditions are given by here. Now, from these equations, I will try to extract the near wall behavior of the boundary layer flow. So let us start with the momentum equation. So momentum equation gives is basically u del u by del x and v plus v del u by del y plus u infinity. Now u infinity can be a function of x, or if u infinity cannot be a function of x. So we do not cast anything over here. No assumption is casted over here, and we assume whatever be the u infinity behavior, we will take it out. Now, if and plus the viscous part, the diffusion part. Now, if I apply this equation on the wall, that is y equal to 0, we get this equation. Now, where u is also at y is equal to 0, the first order velocity gradients are also at y is equal to 0, v is also at y is equal to 0. Now, u infinity into du infinity by dx is a term which is from the outside of the boundary layer. So this cannot be forced on the wall, but since u is small u is a function of y, so mu naught into del 2 u by del y square, that it is the second order gradient of u velocity, can be evaluated on y is equal to 0. Now, since u, because of the no slip boundary condition, u and v both are 0, so this equation turns over here, turns into this equation. Now, since the u and v is 0, so the LHS of this equation becomes 0, so that means that del 2u over del y square will be equal to minus times of mu infinity by u naught into du infinity by dx. Now, if I apply this same boundary layer theory, this equation, if I use the Euler's equation outside the boundary layer, uh, this will result into 1 upon u infinity dp by dp dynamic by dp dx, which is outside the boundary layer. Now, so this clearly shows that the curvature of the u velocity at the wall is basically dictated by the streamwise convective acceleration outside the boundary layer, and for that matter the pressure gradient outside the boundary layer. So now this is very important, that is the curvature at the wall is basically dependent upon the external pressure gradient, streamwise pressure gradient, which is being applied at the external pressure gradient which is outside the boundary layer, influences the pressure gradient outside the boundary layer, basically dictates the curvature at the wall of the velocity profile. Now this is very important to remember. Now if I again try to use these equation, so so this is the top equation is basically what you get, that is this is the same equation which has been repeated before. Now there can be three kinds of pressure gradients. One where the pressure gradient before and after the flow is uniform, that is dp by dx is 0. One where pressure is helping the flow, that is the favorable pressure gradient, that is pressure is high at the upstream and less at the downstream, so that is accelerating boundary layer. Or the pressure is low and upstream and high downstream. If this is the condition, then the boundary layer can be deaccelerating. Like if you have, if in a converging diverging duct, in the converging portion, the pressure will always be higher upstream and lower downstream. That means you will always be having having a favorable pressure gradient in the converging part. But in the diverging part, you will get you will get always get a adverse pressure gradient, because pressure will be higher on the downstream part and lower in the upstream part. Similarly, if you have a flow over a circular section, circular cylinder, in the top part, in the starting part, pressure will be higher, pressure will be higher. Then it will be, and then as you go towards the top of the, sorry, edge, I should say it like this, and the pressure will be higher at the front side of the cylinder. As you go to the top, as you move to the top, the pressure will become low. And then if you again go back to this flow, go back to the, on the right side, the pressure will become small, will again rise to now this will only, and this is the case for the inviscid flow. So at the starting, no, normally the flow is inviscid. So yeah, yes, so this happens like that. So if dp by dx is less than 0, that is the favorable pressure gradient, then and this will happen when du by d infinity is greater than 0, then the boundary layer will be accelerating, will be always accelerating, and the velocity profile, the curvature of the velocity profile, that is del 2 u over del y square, will be less than 0. Now if du infinity by dx is 0, that is a uniform flow. Flow is not the external velocity, that is u infinity, outside the boundary layer. It doesn't changes with the in the streamwise direction or any direction. Then du infinity by dx will be 0. That means dp by dx is 0. That means the boundary layer will be neither accelerating or deaccelerating, and we call this as the zero pressure gradient boundary layer, or ZPG boundary layer. Here del 2 u over del y square will at the wall will become 0. Now if the adverse pressure gradient case is there, then du infinity by dx must be less than 0, which implies that the pressure gradient outside the boundary layer must be greater than 0. So therefore, the adverse pressure gradient gives you into a degree accelerating velocity profile, and the curvature of d2u by del y square must be greater than 0. Now you must also remember that whatever is the pressure at the outside the boundary layer is basically same inside the boundary layer, and that is because the momentum equation for the y direction reduces to del p over del y equal to 0. So there is no pressure gradient in the y direction. So therefore, whatever is the pressure at the outside the boundary layer will be inside the boundary layer also. Now let me explain the boundary layer behavior. The whatever I have discussed in the last slide, or more detail with the help of graphics. So this is the velocity profile of the figure A, that is for the deaccelerating, so for the accelerating boundary layer. So you can see that at y is equal to 0, my del 2 u over del y square is less than 0, and again at the outside here, that means nearly at the u infinity, the velocity profile will be is again which again becomes nearly straight. The del 2 u over del y square is still negative, and the flow is always accelerating. Now if I take a zero pressure gradient boundary layer, as you can see that the velocity gradients are not that much steeper near the wall, and you get a slightly monotonic velocity profile. And since at the u infinity, del 2 u over del y square is still less than 0, and at the wall del 2 u over del y square is equal to 0. But if you consider this case, that is the last case, where del 2 u over del y square is greater than 0 and at the wall, because the pressure gradient is du by dx is 0, that means in this case the pressure gradient is adverse, So you can see that. So at del 2 u over del y square at the u, at u infinity must be nearly must be less than 0, but at the wall it is greater than 0. So therefore there must be a point of inflection where del 2 u over del y square must be equal to 0. Okay, now if this is the case, what can I say about the first derivative, that is del u over del y at the walls? Now you can see that, as I have already shown, in an accelerating boundary layer, the action will be more in near the wall. So that means del u over del y will always be higher, or the highest, for the favorable pressure gradient, and will be the del u over del y will be smallest for the at the wall, will at the for the adverse pressure gradient, and zero pressure gradient will lie in between of them. Now if I consider figure C, let me explain it more. The u velocity profile for a retarding boundary layer, as I have shown, this boundary layer will be called as the retarding boundary layer, and it will exhibit a point of inflection below which the del 2 u over del y square will be greater than 0, and above which del 2 u over del y square will be less than 0. And it also implies that del u over del y increases with y and becomes maximum at y is equal at the point of inflection, and then decreases with increase in y. Now since u is decreasing, that is, it causes the adverse pressure gradient, because capital U infinity, that is the outside boundary layer, is decreasing. At some station y downstream, the del u over del y can become 0. Now this is the point of inflection of the separation. This is the point of separation of the boundary layer. As the flow near the wall reverses the direction beyond which reverses the direction at reverses its direction beyond the point where del u over del y is equal to 0. Now beyond this point, that is the point of separation, the boundary layer equation ceases to apply. Now this is all slightly mathematical description. I will try to explain now with the help of easier physical explanation. Now, so for that we need to consider this slide. As you all know, there is a boundary layer over a flat surface. So the boundary layer divides the no viscosity region and viscous dominant. So I am not going to explain that. Now this is the same thing which I was explaining him. Now if there is a zero pressure gradient boundary layer, that means the pressure in the streamwise direction del p by del x is equal to 0. It happens when it has a constant pressure. So I have plotted the velocity profile. If you see the second velocity profile, that is the case for a favorable pressure gradient. So the pressure uh, is high um, is high at the pressure is high in the upstream. So I forgot to mention that I'm discussing one section of the velocity profile. Okay, at, okay, so the pressure at the pressure at the upstream is high, and the pressure at the downstream is low. So this creates del p by del x negative. That is the favorable pressure. So we are not yet talking about why or how this pressure gradient is created. So you need to suppose that if you have a high pressure gradient or a low pressure gradient, that is a favorable pressure gradient, the these type of pressure gradients can be created in a flow, and we will explain you how it comes. So if you compare the zero pressure gradient boundary layer boundary layer which I have shown with the high pressure with the favorable pressure gradient boundary layer, you can see that this the steeper boundary layer is formed in the favorable pressure gradient. That means the more del u over del y near the at the wall will be always very high. Now, if you consider a case with adverse pressure gradient, uh, this will be the form where there will be a slight negative backflow occurring, and because of the low pressure gradient and high pressure gradient now the adverse pressure gradient tries to create a backward flow, while the inertia is trying to force the flow outside. Now this may result in a slightly backward flow. Now you need to assume these things. So there are going to be three cases over here. So this is the next. So this happens if you see this last velocity in this last slide. So this is the case where there is no separation. But if you try to build this type of a flow, if this type of flow goes slightly further, there will be a slight negative reversing of the flow. So that is what I have shown in the adverse pressure gradient profile. Now, and this is not what we have seen. Let us compare from the exact solution behavior, which I have already shown to you. So in our second unit lecture, we have covered this part, and like in a coed flow, and I am just comparing the velocity profiles for the coed flow, coed Poiseuille flow, and coed Poiseuille flow with the boundary layer flows. Now you see that if the pressure gradient is 0, that is constant pressure gradient, so then the flow will be only Poiseuille or only coed flow, not the coed Poiseuille flow. So velocity will have velocity profile is just the linear velocity profile. There is no parabolic kind of a velocity profile which exists in a boundary layer flow. Now in this, what is the difference between the coed flow is that the top plate is moving with the velocity u infinity, and while the bottom plate, which is shown by the red lines, are fixed. Now in the coed Poiseuille flow, apart from the movement of the velocity profile, there is a pressure gradient also. Now if the pressure gradient is favorable, then you get a velocity profile which is slightly more steeper, and the steeper flow, a large pressure gradient is large velocity gradient is available, is shown in the wall, is the large shown large velocity gradient can be shown over here. You can see that if the velocity profile is made here also, I have made it slightly more denser and than the other case. Now if I go to the adverse pressure gradient profile, so you can see, you must remember that there is always a pressure gradient at which there is no flow. Pressure gradient, you can calculate a pressure gradient where there is no flow in the channel, and between the two plates there is no flow, and if you increase that slightly further, there will be a slight reverse flow. So we have seen the reverse flow before also, and you can fairly conclude from here that reverse flow occurs where when the pressure gradient is adverse. That is one of the primary conditions for occurring of the reverse flow. Now I will show you another um, slide. Now let us assume, now in this slide, um, I will show you a velocity profiles across. Yeah, let us consider curved surface, which is shown by a red line, and the green lines in this whole diagram uh, will be will be will represent inviscid fluid flow, and the pink lines will represent the viscous flow. Now we considered three sections: one at the top, other two at the sides. So if I draw the inviscid velocity profile, it will be just a uniform velocity over here, as I have shown. so this is the velocity profile at the top, and this is the velocity profile is at the bottom. Here the u infinity at the top, at this side, and on the right side, left and right side, because they are symmetric points, they will be symmetric. The velocity will be symmetric. At the top, the velocity will be larger. Okay. Now, if I try to see from the my from the inviscid theory, the pressure will be higher at the left side, and while the pressure will be lowest at the top side, and will again regain at the same value at the right side. So this will be the inviscid flow, and on this inviscid flow, I will try to draw this velocity profile. So you can see that I have drawn the velocity profile over here. So the velocity profile is very clear, and over here, and now I will draw the velocity profile over here, which is the top. And now I will now if you can see that from high to low velocity profile, from this top left side and to the top right side, the pressure gradient is favorable, while so there can be no reverse flows, as I have already shown over there. Now, but for what happens at the other half? At the other half, the pressure gradient becomes adverse, not immediately, but at the it becomes adverse from whole of the side, and this is from the inviscid theory. Yeah. So the pressure gradient. And I have already told to you the pressure gradient will be all in a boundary layer flow. The pressure gradient is from the inviscid theory, and pressure gradient is dictated by the inviscid theory, and this pressure gradient dictates the flow inside the boundary layer. Now, if I try to draw the velocity profile at the right side, and as I have already said that when there is a adverse pressure gradient, the extreme condition will be that there will be slightly reverse flow. So, and this is because the and back at the backflow, the and at the back, the adverse pressure gradient is there, and hence the reverse flow can occur, while at the front the adverse there is a favorable pressure gradient, so no reverse flow can can seem to exist. Now, so if I let us see what happens over here. Now, if I try to see a fluid particle, the fluid particle, so this fluid particle will try to move from here to here, and if I try to see the fluid particles at this side, that is at the after the from the reverse side, the fluid particle will try to go from here to here. So there will be a kind of place where these two interact, and since they cannot push downwards, the flow the particles will try to move upwards. So this is going to happen. So at this point, if I try to draw the velocity profile, uh, there will be a place where at this point, if I try to draw the point, draw the velocity profile, so this will be like this, where if I magnify, you will see that there is a del to u over del u over del y is 0 at this point, and this is called as the point of separation. Now, if I try to draw a streamline, you see that since the velocity this curve, so if I trace the path of this curve, this gray curve, that is the velocity per particle of try to trace the path of this particle. So it will go from here to here to here to here, from here. This is good. Then it will try to it will encounter these velocity profiles, which are these particles which are coming from the back side, and since it is at this point, after this point, the particle has to move upwards, so it will go try to move upwards. Now, if I try to draw another streamline from here, so this will be like this. So the particle is coming from here, and from the back side, and since it is a reverse flow, it is coming from back, and then at this point it will try to go upwards. So therefore you can see that this is the point, this is the point of separation. So as the figure shows this, the boundary layer theory, so the fluid which is attached to the surface of the boundary layer, to the surface of the fluid flow, so the boundary layer is attached to the surface, and then it after the point of separation, it detaches from the surface. Now, and till this point the boundary layers theory applies. Now at the now I have summarized all of this in this slide, where I have demarcated the accelerating region, that is the favorable pressure gradient, as region 1, the zero pressure gradient region as region 2, and the region 3 as the adverse pressure gradient. So as you see that, if I try to see the what are the different characteristics of the zero pressure gradient boundary layer, sorry, favorable pressure gradient boundary layer. So the pressure decreases in the flow direction. That is obviously, that is why it is a favorable pressure gradient. Pressure force in the direction is in the direction is in the flow direction. It helps the flow in attaching to the surface even stronger. Therefore, the flow near the surface has a steep velocity gradient, and it has been shown that the flow cannot separate from the surface uh, if the pressure gradient is favorable. Now, if the pressure gradient has a zero pressure gradients, therefore there is no help from the pressure gradient side, either in deaccelerating or accelerating the boundary layer, nor it helps in the separation part. The fluid particles inside the boundary layer slow down due to only shear stress only. See that now, and the flow cannot separate from the surface. Now, what happens in the last part, that is the adverse pressure gradient part? Pressure increases in the flow direction. Therefore, the pressure force is in the opposite direction of the flow. Flow particles which are close to the wall with low momentum may come to stop or even move in the opposite direction. So if they stop, then it becomes the point of separation, and if it moves in the backward direction, therefore then a reverse flow or the backflow is created. So as you can see that boundary layer separation point is the condition for the separation point is that del u over del y must be equal to y equal to 0. So the boundary layer theory is no longer applicable after this point. This is one of the most important things. So boundary layer theory can only be applied till the point of separation. So what is the other takeaway? One takeaway is this, that the adverse pressure gradient is the necessary but not sufficient condition for separation, and separation will occur only if the pressure gradient is high enough. So these are the two as the these two, and the boundary layer theory is no longer applicable after the point of separation, are the three takeaways from this topic. Now I will try to explain the application of this boundary layer separation or the separation phenomena which have been there. Now, if you see the um first slide, first picture, there is a car, old car, and you can see that the circular part shows you the separation over a car, and you can see that this structure is not a streamlined structure, and another car which is a streamlined kind of a car shows very less separation behavior. There is another aerofoil, and over that aerofoil we see the streamlines, and this airfoil is at a stalled condition. So it shows that the stall conditions, at the stall conditions, the separation is the point of separation is basically comes to the leading edge, then the stalling happens. Separation in a diverging duct is the next case. It is all others are external flows, and this is the only internal flow which we have put it over here. So they see this is in a diverging duct only, not a converging diverging duct, but a diverging duct. So you can see that the separation is there at the third instance, third velocity profile. You can see this, and this is the case where the pressure gradient is adverse. In a diverging duct, the pressure gradient will be adverse. In a converging duct, the pressure gradient will always be favorable. Now you can see that from another flow over a cylinder, so the pressure gradient it is a better picture, and you can see that the boundary layer comes from here, very small thin boundary layer, and then it becomes slightly thicker, and then it separates from the surface. This is the point of separation. Okay, it may be laminar or turbulent. It doesn't depends upon the characteristics. So the point of separation depends upon whether the flow is laminar or turbulent, but the occurrence of point of separation is independent of whether the flow is laminar or turbulent. So the boundary layer theory is entirely a laminar phenomena. Many people confuse it with the turbulent flow, but it is not necessary only in the turbulent flow. Now, since in a laminar flow, the kinetic energy of the fluid particle is lesser than the turbulent flow, so there is a ball. It shows that there is a ball, and the flow separates much before this. And in a turbulent case, the boundary layer separates much later. So this sudden and this happens very suddenly. So people have recorded this characteristics, and they show that the CD is the drag force, and if you plot with the Reynolds number, it increases, decreases, and then becomes constant, and then it drops suddenly, and then jumps up. So this sudden drop is due to the flow becoming from laminar to turbulent at this Reynolds number, and this sudden drop is called as the drag crisis. So at this point, at this Reynolds number, so the point of separation is goes from something around 90 to something around 135. Thank you.